So I've discussed how a latch is basically a bit of memory, and we've discussed how complicated transistor logic, complex transistor logic, needs a clock signal to proceed in an orderly fashion, and a clock signal turns a latch into a flip-flop. So let's see how we make an SR flip-flop. So how would we go about designing something like this? Well, we use logic gates to understand it on a more simple level, and we can do transistors to implement the logic gates. The feedback works just fine. So our simple SR latch is our two NAND gates and our two inverters. Now, why am I not using the NOR version that we did to get rid of these inverters? Hold on. We have our set signal, which goes into one of the gates, our reset signal, which goes into the other gate. The outputs are, of course, Q and not Q, and then the standard cross wiring that gives the circuit its magical, wonderful feedback. I really could draw that better. We'll just do it that way. The inputs to this gate are S and not Q, and the inputs to this gate are R and Q. Well, not S and not Q, basically. So when S and R are both 0, that's essentially saying don't change the flip-flop, right? Don't change the output, don't change Q. So what we want to do is to say we want this to never change unless we're giving it a signal. We want a signal, let's call it E. Let's say we have a signal E for enable. So enable would be more like a flip on and off. When enable is on, you want it to change, and when enable is off, you want it to not change. A clock is just an enable signal that goes on, off, on, off, on, off, on, off. So that's just it. It's an enable signal with a regular frequency. That's your clock. Well, what's the simplest way to say, okay, if enable is 1, then logical 1, obviously, then S and R should be passed through like normal. If enable is 0, then S and R should be whatever they can be, and nothing will happen at all. Well, looking at it with logic gates, if set and enable are both 1, then 1 should be passed into this inverter. Otherwise, if set is 0, then we're not trying to set, so the output should be 0, and if enable is 0, then we should be ignoring set, and the output should be 0. That's an AND function. It's 1 if and only if both S and E, set and enable, or clock, are 1. So all we need is two AND gates. So we have our set signal that goes into this AND gate, our reset signal that goes into this AND gate, and our enable signal that's the other input to both, which gets inverted, gets input as not S and not R. In this case, it's set and enable not, and this is reset and enable not. We have Q coming out of here, not Q there, just as normal, and then not Q input to there, Q input to there. All we've done is added these two AND gates, very simply saying enable and set have to be 1, reset and enable have to be 1. Well, we've got and inverters. Well, that's just a NAND gate, which is good news because with BJTs, AND gates don't work great, but NAND gates do. So that's why I used the NAND version, because now I can just sync these inverters right into these gates, and the whole circuit just uses NANDs. So once again, our set goes in there, reset goes in there, enable goes in both. These are set plus enable not, set and enable not. This is reset and enable not, Q, not Q, not Q, and Q. Nice and simple. So this is our flip-flop. Enable has to be on for anything to go into the latch, so it's control plus latch equals flip-flop. If enable's on, then the inverted signal goes in and the flip-flop can change. If enable is off, it can't. So basically you would have your clock pulse. When your clock pulse turns on, when enable goes high, then this layer of the logic gets processed. And then when it's off, it doesn't. So what you might have is a staggered clock signal. You might use a frequency divider or something where your clock is going pulse, 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 pulse. And let's say you have layers, and you might say these two layers on one clock pulse, these two on the next, then these, back and forth if you have 4 layers. So no layers are touching that will change at the same time, which means they're not going to get conflicting answers. I'll go more into that when I actually implement layered logic with transistors. For now, it's just There you go. Now you might say, okay, this takes 8 transistors. Let's use standard NPNs. 2-input NAND gate is 2 transistors. So 2 times 4 is 8. But you can actually do it with 7 because the enable signal is shared with both. If you're doing these logic diagrams, if you're using this symbol, there's no way to really say we can use 7 transistors. There's no transistors here. You can implement this however you want. So let me show you with transistors. So here I have 4 2-input NAND gates, 2 NPN transistors in series. So let's say we have set going into this one and enable going into this one. So that's the first NAND gate. Let's say we have reset going to this one and enable going into this one. So that's our second. And then let's say the output here is A and B, just because I'm running out of space. So this is the first output NAND gate, so this would be Q, and this would be not Q. So the inputs to this gate would be A and not Q, and this one would be B and Q. So these are the 2 NAND gates on the left that take the clock signal and give A is set and enable not, and B is reset and enable not. And then these are the 2 NAND gates on the right, the top one giving Q with the set signal, the bottom one giving not Q with the reset signal. So right here, this is your flip-flop, it works. But since we're using BJTs in series like this, it's all about conducting. When enable is on, when enable is high, this NPN is conducting, which means this NPN is being allowed through. Think of enable as a gatekeeper. So if enable is low, that's closed off and it doesn't matter what set is. It's going to be closed and we're going to get our high as A. If enable is open, if enable is high and this NPN is open, then it matters what set is. If set is low, this NPN is closed and you get a high as A. If set is open, if set is high, then the NPN is open and you get low for your A, NAND gate. So all that matters is that enable acts as a sort of gate. So what if we do this? What if we have 1 transistor? Enable goes into it, and both set and reset pass through it. The outputs are up here, remember. If enable is low, which means this NPN is closed, then neither of these are going to conduct no matter their setting. So A will be high and B will be high. If enable is conducting, if enable is high and this NPN is conducting, then it's essentially not there. Remember, because the collector to emitter is very close to a 0 voltage drop. So it's as if it's a wire there. So you just have set and reset, but they're controlling things separately. Think of your Kirchhoff loops. You can go from this positive through the resistor through an open NPN to negative and back to positive. Both of these loops share only this transistor here. This is the only element that's in both of these loops. So if the voltage drop changes over collector to emitter somehow, or if there were a resistor down here, then both would change based on that. But this is pretty much going to be on or off. So we're going to get a high or low through this loop and through this loop. So it's a separate piece of the circuit that can have different outputs, sharing 1 transistor. That is the gatekeeper. So here's your SR flip-flop with only 7 transistors instead of 8. Now, one thing to keep in mind when you're using BJTs, remember how I was having trouble where these SR flip-flops, SR latches would not give the low and high? It would be like 0 volts and 0.7-ish volts. It's because of BJTs and feedback. Look, if Q is high, let's say this output is high. So you would expect to have positive to the resistor and out to Q, and whatever's connected to Q, and you would just see high. But instead, we're going to see like 0.7 volts here. The reason for that is Q is coming in through here in a BJT. With MOSFETs don't really have base current. They are effectively closed circuits. So if you were using MOSFETs, like your little ICs, your integrated circuits that have MOSFETs inside, CMOS, CMOS, then this would work. Your Q would be high or low, and that would be it. But with BJTs, there is base current. So look at our Kirchhoff loop. Positive through the resistor, out Q, Q into base, emitter to negative. That is a single Kirchhoff loop, so we can say we know the voltages. We don't know exactly the voltage drop of this resistor because we don't know what else is connected to Q, but we do know one thing. That's why Q ends up being a diode drop, because negative emitter to base and out, and this resistor is taking the rest. Because there is current here, it's locking in the voltage of the output. So that's one thing when I show you latches, flip-flops, and all this other circuitry, when we're using BJTs, this is something we have to keep in mind all the time. If there's feedback, you're going to get this goofiness issue. This latch using NPNs has to be plugged into NPNs. If you plug it into PNPs, it's not going to work. Now you could change it. These are NPNs in series making NAND gates. PNPs in parallel also make NAND gates. So if you want to drive PNPs instead of NPNs, you could change this to PNPs and just put them in parallel, and there you go. But that's something to keep in mind for this input. What if something else is driving this input, something that has this same issue? This doesn't. This does not have feedback. This is giving you your nice, clean high or low. So it can drive NPNs or PNPs. So you can switch this however you want. But what if the input requires driving NPNs or PNPs? This is the NPN version. Well, once again, this is a NAND gate, so NPNs in series. We can make it a NAND gate with PNPs in parallel. It's just a little trickier. Just to give myself more space, I'm going to put the SR latch over here. This is how you're going to see these latches and flip-flops drawn as units. We have S naught, R naught puts out Q and not Q. And it's just 4 pins. Well, an actual one would have 6 pins because you'd have your VCC and ground, but anyway, that's implied. So this is just the latch part. This is the 2 NAND gates on the right. Right? Doesn't matter how it's implemented. We established that would drive both NPN and PNP and MOSFET and all that stuff. So the latch is the latch. However you implement it, it doesn't matter. So into here, we would put set plus enable not and reset plus enable not and enable not into the latch. So now we get those signals. So here's our 2 PNP NAND gates. They're in parallel and the resistors down here. We put our set signal in there, enable in there, reset here, enable here. Out of here is set and enable not. And out of here is reset and enable not. If set and enable are both high, both of these PNPs are off, which means set and enable not is low. And that's what we want active, see? Because we want not S, so a not S should be 0 when we want not S to be active. If either set is 0 or enable is 0, then one of these is conducting, which means high, a 1 is getting through here, which is going to make the latch ignore that input. But once again, we have enable as a gatekeeper. And this one is less intuitive, trying to merge 2 different parallel setups, but it's not as crazy as you think. Let's ignore enable for a second, and we just have the inverter. We have our set signal, we have our reset signal. So this would be as if enable were always on. If enable were always high and we had a PNP here, that PNP would be off. So it would be just set determining whether or not the signal was passing through, or the power was passing through to set this output to high. And let me actually flip this around. Let's put reset over here. And let me add just one more PNP. We'll give it some power, we'll give it the enable signal, and then I'll connect it to both, just like that. So let's say that enable is high. That means this PNP is off, it's not conducting, so it's as if it's not there. If it's not there, then we had what we had just a second ago. Our 2 little loops that don't matter that E is there, that this PNP is there. We just had 2 inverters and it's as if, there you go. Let's say enable is low. Then we have positive through the PNP to the output, to the resistor, to the negative, and back to the positive, an isolated loop. Enable being low means that this positive is getting connected directly to the output, which makes the output high, and it doesn't matter what either of these are doing. Both outputs are going to be high. This can conduct or not, it doesn't matter. This one's conducting, but they're not conflicting. They don't fight over each other. It's still a parallel setup. It's just shared wires. So once again, with PNPs, we have 7 transistors for an SR flip-flop. So now you can see you can use NPNs or PNPs for the control part of it. So if you have a previous part that requires NPNs or PNPs to be fed, you can mix and match. But this section has no feedback, it has no shenanigans, which means you're getting your clean highs and lows. You're getting your 5 volts or your 0 volts, or whatever volts, which means it doesn't matter whether this uses NPNs or PNPs, they'll both be driven equally. So you can change this part based on what BJTs come before, and you can change this part to what BJTs come after, and they're both modular in that way. And you'll see with future flip-flops, And as we start combining flip-flops, they're all modular like this. You'll have a control segment and a latch segment, and they kind of mix and match. But this method we used is something to keep in mind when you're designing a circuit. First, design the circuit without any idea towards optimization, right? We just did our logic gates and didn't worry about it. Then we implemented with transistors and we saw, oh, I can have these two transistors combine into one and be shared. Don't try to optimize early. It's the same for computer programming. Design well, design reasonably, but don't try to optimize. Just make a good design that seems to work well. If you can eliminate a logic gate, eliminate it, whatever. Take your NAND with all these inverters, combine them and switch to NORs instead, that kind of thing. But once you've simplified the overall design, then go to your actual components and you'll see other ways to optimize after you've gone through the design process. You'll save yourself a lot of grief and time by separating design and optimization. So next time, I'm going to get into more advanced flip-flops. And as I've said, the SR1 is the only one I'll really show as a latch. Everything from here will be flip-flops because there's always going to be a clock signal. But while I let you digest this, I'll be seeing you.